I've been working in the space industry now for a couple decades. My first company was called Made in Space. We did the first in-space manufacturing. And what I learned there is that space has a space problem, meaning there's not enough usable space in space, or not enough real estate to do anything or do a lot of stuff in space for like tourism or entertainment or in-space manufacturing and production and biosciences and pharmaceutical production. And so MaxSpace, in the name, I like to name things what they do, is trying to get the maximum amount of space in space at a cost-effective solution.
Hey, SpaceWatchers, this is Space Café Radio, your channel about trends, awesome events, and interesting people in the space sector. Sometimes you get these opportunities that you can't plan for. But hey, this is one of the reasons to go to conferences, the serendipity of the moment. In that case, I crossed paths with Kemmer for about 2 seconds at the Space Symposium, and I just heard, "Hey, Torsten, let's talk." Sure thing, I'm up for it. What I didn't expect it was this deep dive into expandable technologies and their usage in space and on Earth. I spoke with Maxim de Jong and Kemmer of MaxSpace about their products, about Transhab and the future of humanity in space. Apologize for the slightly longer episode than usual, but you will hear why. I'm Torsten, publisher at SpaceWatch.Global, and here's the story. Lean back and enjoy. Today I have with me here Maxim de Jong, and later on he will hopefully join us Kemmer from MaxSpace. And Maxim, starting with you, how are you doing today?
I'm doing absolutely great. There have been no problems with our production on the latest production of our space module, so I'm very happy.
Where are you based?
This production facility and the development, we're based about 1.5 hour drive east of Vancouver, beautiful Vancouver, British Columbia in Canada.
Wonderful. That sounds fantastic. Tell us a bit, before we dive into the product and what you guys are doing, a little bit about yourself. Tell us a bit about your background. How did you migrate it into a space nerd as you are today?
I guess I would qualify very much as a space nerd and an industry insider. One of my favorite sayings is, life is what happens while you're making other plans. And I think this is a typical example. I am not originally an engineer, aerospace engineer or spacecraft engineer at all. My original studies were in biophysics, very strong math physics background, but I hated school. I'm a field guy. When I left university, I basically spent about 15, 20 years consulting for remote environment access. So mining companies, high altitude mining companies in the Andes, how to rescue people that got edema, anything that would be a difficult access for commercial applications, anything in the mountains, deserts. So I used to work about 15 countries all around the world. And we developed our own fabric structures, harnesses. I personally specialized in a lot of helicopter work where you would hang from a long line from a helicopter. We developed the ropes. We were the first to use fireproof ropes, etc. Worked together with a German company to develop that. So we were specialists in really high-tech harness and rescue systems, for example. And NASA was having problems at the end of the Transhab program with the integration of Kevlar high-performance strap. They wanted an inflatable structure. How to integrate this with the big docking bulkheads, the metallic infrastructure that all spacecraft are generally based on. And that technology that NASA developed for the NASA inflatable Transhab was then transferred to Bigelow Aerospace. They continued having problems with the straps breaking where they attach to the docking bulkheads. The Kevlar straps were breaking at very low loads because of the fiber property. They went to their mill that made the fabrics and the webbing and the straps. They said, isn't there anyone who can, help us solve this problem? They sent straps out to all the standard US suppliers for military and spacecraft, and they were having very difficult, very poor results. Then they finally heard of this company in Canada. That was me. And I think that was the last month of 1999. And I guess we solved that issue for them altogether. And then the rest is history. Ever since then, I was like, oh, this is so cool. Absolutely fantastic. And that's where we got involved with the space business.
And now moving fast forward at the recent Space Symposium in Colorado Springs, you came, at least for me, out of the stealth mode with Max Space and introduced the inflatable structure thing. Can you guide me through that? What is unique on that and why now?
Great question. You've done this before, but the reason at Space Symposium we came out with Max Space, Aaron really is the impetus behind Max Space specifically. I get to be the technical guy, but Aaron is focused on the commercialization. He saw that my company here, Thin Red Line Aerospace, we built the pressure hulls for the Bigelow, Genesis 1 and 2, the only ones that ever flew as a free flyer. That was developed here. Design work for Beam ultimately. So it's a long heritage. He said, why isn't this stuff in space? Because obviously you've come up with technologies and you have more experience doing this than anyone else. And I thought that sounds very rational. I loved what I was doing. We've had roughly 40 NASA programs we worked on, but it's all deep space, very esoteric exploration, heat fields for Mars, human Mars entry, Venus balloons, Titan probe, that type of R&D and tech development. So I'd like to see something fly before I'm gone. So it was very enticing to listen to Aaron and his thoughts for commercialization. Low Earth orbit, it's a sandbox that's becoming commercialized. Commercial low Earth orbit, it's called, the program, NASA. And we've been developing the technology or not advancing the technology, but getting it in a format that we can launch quickly, efficiently, as a first tech demonstrator of the stuff that we've developed over the past 24 years.
Help me. So you developed these kind of structures before with your company for Bigelow, as you mentioned. That stuff flew. So there's this heritage coming on. But why isn't Bigelow driving that forward and using your technologies?
That's, once again, a good question. Mr. Bigelow, he had an amazing vision. The only problem was he was about 20 years too early in a way, because the problem was availability of launch vehicles big enough to carry out his vision for 300 cubic meter plus inflatable hotel modules and so on. He managed a very amazing fast track program where I was able to do anything I wanted. Genesis 1 and 2, they flew successfully in 06 and 07 on Russian launch vehicles. They were converted ICBMs from the Cold War, and they were very successful. They are still orbiting Earth to this day. Now, what the big paradigm shift from my point of view, and this is the crux of the whole issue. On one hand, we have a very skilled team here with immense amount of experience. We did like 20 high space grade modules for Bigelow pressure shells, burst tests with window frames, with all the things that other people are working on now. So we've got a 20-year head start. The big issue from a technical point of view is that it's a fabric structure, and the original Bigelow and Transhab designs, while they were extremely cutting edge at the time, the problem is that to get the safety level you needed for human occupancy, ultimately, the safety factors needed to be very high to make sure that all the fibers would be loaded correctly and that there was no chance of anything going wrong. So with Genesis, we flew safety factors that were, the hull needed to be 8 times stronger than what we really needed for a human, just for the comfort level and the engineering safety factor needed. Beam, the inflatable Bigelow module on ISS currently, I believe it's well over a 10 factor of safety. The problem that we have with that is this giving inflatable habitat architecture a black eye. Why would you want to have an inflatable habitat when you could make, with access to current launch vehicle sizes, why don't you just make a metallic structure that's bigger on Earth? You can outfit it the way you want. You don't have to worry about whether it's going to inflate on orbit and look like a laughing clown. It's a joke, but it's much easier to do on Earth to make sure, and then you don't have to worry about how it deploys. With the mass involved with those earlier, inflatable habitats, my thought would be, even though I love inflatables, it would be a tough sell. I'm a field guy. So from a commercial point of view or going to NASA headquarters, I'd say, well, it's really cool, but really, we want to have something that, we want it big, but how can we justify, it's pretty heavy still, and we have lack of predictability. So after Genesis flew, I embarked on burning through all our personal resources, business resources. It nearly put us out of business. I'm totally serious. But there had to be a better way. And what happened with Thin Red Line Aerospace here, we stumbled across, not due to immense creativity, we stumbled across more of a mathematical anomaly in how you could align the fibers in a more predictable way. And the invention goes all the way back to Bernoulli in 1692. It's an amazing history. I won't go into those details. But the bottom line is that at this point in time, and NASA actually funded the biggest part of that research that we've done over the years, once we showed them that, hey, we have something that we developed with our own funds. Look at this. What do you think? And that has proven to be extremely highly predictable, immensely reproducible. And one of the best features is you can scale it to the giant sizes that we ultimately need, quasi-indefinitely. And that's a holy grail in expandable architecture. You want something that's 1,000 cubic meters. How do you flight qualify that? How do you qualify it for human use? That's ultimately a crux. And that's something that I believe that we've been successful at solving that problem.
If I recap that the correct way, so you are able with your technology to have quasi infinite sizes of inflatable structures, whereby infinite is at the moment limited by the transport vehicle to get it up into space. Right? And then potentially you will then connect modules together to build something bigger out of it. Is that the idea? So my work?
Yes, that's the general idea. If you speak with space psychologists, my wife is actually a psychiatrist, so she should chime in here. But the issue with long-term habitation for humans getting along and being able to actually exist for an extended period of time, as an design engineer, I'm surprised at just how much room is actually truly needed. And we're just talking about the human element. If you're 7 months transit to Mars, for example, the requirements for mental safety, for mental health, it requires a lot of volume. And we're not even talking about multi-year habitation, off-planet habitation. And then we're also not talking about, in support of human existence off-planet, what about the infrastructure that's needed for fabrication capabilities, basically warehousing or controlled environment for everything from structural fabrication to pharmaceuticals to you need a lot more room even than what Starship, for example, would be able to provide us.
Can you put that rationale into a relationship for me when you said you need a certain amount of volume to travel a period of time? So how does that relate over time? So how much more volume is needed over X amount of time? Because we know all the picture when astronauts on the Soyuz were squeezed in and then flew 3 days actually without moving in this small capsule and then docking on the space station. But I'm curious to understand how this relationship between long duration / settlement and space comes together.
I'm not qualified to answer that. All I know is what is being fed to me when it comes to, okay, Maxim, you need to be looking at this. You need to be looking at that. These are problems that need to be solved. Okay. We can have, different modules that are linked together, for example. But ultimately, that's from an engineering point of view, it's very secure to have modules of 300 cubic meters. They're connected, let's say end to end, hypothetically, so you can firewall them if something goes wrong with one of the modules. This makes engineering sense. But then I get the response saying, 300 cubic meters, there will be limitations on how long there would be, psychologically speaking, we would need larger volume, a greater expansiveness of the architecture for long-term mental health. To say exactly what size or how correlates with what duration, you were very incisive, but that would be beyond at the moment something that I'm aware of. I have had the comments that, 500, 600 cubic meters for an individual unit to give a feeling, sensation of true habitable environment would be a baseline.
I think we humans are not used to think when we talk about space in cubic meter. Try to translate it. So 300 cubic meter for a room height of 2 meters are 150 square meter. What I would consider, it's a good size. It's about the size that we have in our house here.
Yes, but if you were left there for a long period of time, and as you mentioned yourself, I hear the bird outside my window, it's a vastly different. I grew up in Europe and we were in a small row house. You know what that's like. And I came to Canada when I immigrated, the vastness. So this comes back to the thing, what you mentioned about the Soyuz. You're dealing with highly trained, highly disciplined individuals that have been through significant screening. If you want to have scientists go, or somebody that resembles a mere mortal outside of the discipline and the training, it's a very different world. I know that from the high-risk activities from my past consulting in remote areas. I would take someone who that's not what they do, and you bring them into an environment and the psychology is extreme.
I think it's hard to imagine for any of us to just sit for 20 hours in your seat without moving. It is where it starts. Of course, we all had long-haul flights in economy, potentially. We know how it feels, but even there, you can stand up, you can go to the restroom, you can, walk around and then squeeze into your seat again. But sitting there for this extensive period of time, as you mentioned, it requires this brutal discipline to yourself to go there. And that in a very hostile environment where you don't have this space. You have space, but it's the other space, the emptiness of space.
Yes, I think you gave a very good summary there. It gives you goosebumps when you think of it that way.
Tell me, the inflatable modules you are now building with MaxSpace, what is different? What is unique?
So it goes back to the predictability of the design. Again, the TransHab design, and I would love this to go somewhere for the record. What NASA did with TransHab was amazing. If anybody knows high shell load fabric pressure vessels, this is the place.
Can you help our audience to remember what TransHab was? Because I'm quite sure not everyone has it on his radar, including myself.
Right. Thank you my nose is on this. So I'm glad. Thanks for bringing me back into the proper orbit of the big picture. I had that question in an interview yesterday. Why did it take so long for inflatables to come on? Because it's obviously a very interesting solution and a very valid one. It's now been demonstrated. But the issue is that the concept of having a fabric structure in space is such a paradigm shift from the nastiness and challenge of the space environment. How could that possibly be? At any rate, NASA in program in the late 90s, they were thinking, they were ahead of the game. They were real leaders with coming up with this notion of, we can get something bigger. We need this for the psychology. That's what it was about. And NASA already identified, we need something like 300 cubic meters, something like that. And that's what our Bigelow full-scale modules were patterned after, was after NASA TransHab. TransHab was for long duration human existence in space. Mars transit habitat. So that's where the TransHab name came from. If we want humans to exist long enough without attacking each other with knives and forks in transit, for example, to Mars, we need a big volume. How do we do that? we can get very strong materials, straps, Kevlar, mil-spec, military certified. We're going to make an inflatable. And by golly, they did. And they did so successfully, like very quickly. For me, it reminded me of the Apollo era. The stuff that was done and flown in short order. Absolutely. It's almost like with our current risk-averse environment, it's almost impossible to rationalize. So what NASA did in a few years, they actually built a 4-over factor safety, so where it's 4 times as strong as it needs to be, at least. They built a totally new technology. It was in full scale. They even did vacuum chamber deployment tests. They put debris shielding on the outside that would actually be stronger than what you would have protecting ISS. And they pulled that all off before the end of the 90s. And again, it's one of the most impressive things regarding space technology development that I've ever seen. And I would love for that to be on the record. Now, the deal is that they use the same design approach that, if I can be bold enough to say, I would have taken at the time too. The strongest fabrics are basket weaves. While fibers going one way, fibers going 90 degrees the other way, that gives you a strong basic coverage of strength. What they did was, this is the basket weave. We're going to replace the individual fibers with a super strong strap, Kevlar strap. And we're just going to weave those, just as if it was like a monster basket weave on steroids. And that worked really well. And that worked so well that Johnson Space Center continued along that design path afterwards with their own funding, with much more limited funding. Because their funding on TransHab was pulled for a variety of political reasons. I don't know the details of which, but it was extremely heartbreaking. JSC continued along that path and validating that design because they got it to work at a big scale. So there's no reason to really deviate. They didn't have any real profound problems. So what happened was Robert T. Bigelow, also visionary, being a billionaire, he bought the rights to the TransHab design, entered the Space Act agreement, and wanted to continue that, but actually bring it up to a commercial entity. That's where I came on board to help with the interfacing with the rigid structure to get the strength to weight ratio up. But the thing is, I'm a field guy. And when I look at this, I say, okay, deploying this in space, it worked here at JSC. They have the facilities. But it scares me seeing all these straps that could shift. We already had that problem with the clevis pins on the bulkheads. How do you make those fibers align just perfectly? So I went ahead or advanced the design. That's maybe not a very nice way to say it, but I thought it was an advancement from an implementation point of view. So we set up special tooling here where we were able to basically stitch all the straps in place, that nothing could move. It wasn't a basket weave. We took the basket weave out and we made the whole structure in one direction, the hoop structure, and it was all edge to edge stitched. And then we made a separate meridional axial direction structure. And everything was integrated so that you could bunch it up and then it would deploy without shifting the fibers. I think it was an improvement, saved about 15% in the mass, something like that. And that's what flew Genesis 1 and 2, and that was successful. But still, the big problem remained. And the big problem was that you had straps going in 2 directions. If you inflate this module and you have a rigid core, for example, inside, which is the current baseline that NASA has been working on, and now Sierra Space, the load sharing between the straps is not super predictable. It's not predictable enough to be able to get the mass and the safety factor in line. In my opinion, that's a personal opinion. That design will fly. There's no problem with that. We're just concerned that the level of predictability and the safety factor needs to be, you need to throw a bunch more mass at it. And then you don't know exactly what the failure mechanism is going to be exactly. Without putting a lot of extra mass into it. That's one thing.
Right.
But ultimately, the biggest problem will be going to big scale. It is not possible to double the strength of a strap by making it double thickness or double width. It doesn't work that way. If you make the strap twice as thick, the weave needs to be different, and you need to recertify for that applicable using that structural element. So that's very big. So our architecture that we worked on for a long time is what's called an isotensile architecture. That's doesn't resemble the original design that we used on Genesis at all. It's not remotely. And there's lots of pictures of it now on the MaxSpace website. I could actually show you in person by rotating this table, and you could take a view of the Alpha full fidelity ground test unit outside my door here.
That's pretty hard on a podcast, on an audio podcast to show, but I'm happy being in Vancouver to pay you a visit. Thank you, Maxim, for this explanation. And now we are welcoming also Aaron here in our virtual room, in our virtual setting here. Aaron, how are you doing?
I'm doing fantastic. Thanks for having me today.
That's great. With Maxim, we just discussed about the fabric and the structural element. So maybe you can jump in and give us the elevator pitch of what is MaxSpace, what happened at the Space Symposium when you made this big announcement, and where all this shall go.
Yeah, it's a great question. So I've been working in the space industry now for a couple decades. My first company was called Made in Space. We did the first in-space manufacturing. And what I learned there is that space has a space problem, meaning there's not enough usable space in space, or not enough real estate to do anything or do a lot of stuff in space for like tourism or entertainment or in-space manufacturing and production and biosciences and pharmaceutical production. And so MaxSpace, it's in the name. I like to name things what they do, is trying to get the maximum amount of space in space at a cost-effective solution.
It's not from Maxim to use his name.
Some people often think that maybe it had like a 20% of it, but just a great name. If like our website, it's getmaxspace.com, because we want to get you the maximum amount of space in space. And so it's very volume focused. That's been the name, as they say. In the beginning, we'll start out with some smaller modules that maybe pack inside of a couple suitcases and expand up to the size of a cruise ship cabin room, which is like a 10x volumetric improvement. Then our next ones will get bigger and bigger. We'll have something that packs into, let's say, 5 cubic meters and then expands up to the size of a space station module today.
Hold on a second. You just said you have a box and that expands then to a cabin size structure?
Yeah, like a cruise ship cabin size structure. 20 cubic meters is like the size of a small cruise ship cabin room. And it goes from like basically 2 Samsonite suitcases.
And that's human ready or just cargo? So what can go in? Because I'm just fascinated by the sheer numbers, and it's hard to imagine on an audio podcast.
Everything we do, we build with the idea of that we want to have humans in MaxSpace modules. That's the whole dream. The first one we won't have humans in, but it'll be more of a technology demonstration in gathering data. And we'll have some low fidelity kind of payloads on board as well. But then the bigger ones, we'll put humans inside. Our goal, our midterm goal is if you can inflate roughly the size of the entire space station in one Falcon 9 launch. And that's pretty game changing, actually. The ISS took like 60 launches and $100 billion to make. But it doesn't stop there. Eventually you'll have Starship and New Glenn and these really large rockets. And with that, you could launch even more volume, a lot more volume, tens of thousands of cubic meters in space, or kind of small stadiums where you could have a lot of applications and fun with them. And so like our whole vision and idea is to provide the maximum amount of usable real estate in space and kind of be the real estate platform. We moved ahead a decade and we were successful at that, then we'd be very happy.
Help me with a question of an engineer, but not someone who is deeply involved in that. If you have an inflatable structure and you need pressure, you need something to fill it with. If you have these huge structures you just mentioned, ISS size, module size of an ISS, you need the air to pressurize it as well, or don't you need it?
Yes, you definitely do.
So that's also something you have to transport then and then to fill it up. Okay.
Yeah, of course.
Okay.
But it should be noted that all stations, human-rated ones, are going to have air in it already anyway. So it's not like an added cost.
The next question, if we look 10, 15 years ahead, is it possible to manufacture, to create this kind of structures in space, for space?
Great question. I've thought a lot about this last company, Made in Space. But just back to the air thing really fast. You basically fly up compressed tanks and compressed air, and then it'll help with inflation. And then the human-rated ones will use like life support systems in the same way that other kind of stations do. In terms of building really large scale, like basically pressure vessels on orbit using like in-space manufacturing and assembly, it's something I thought a lot about at Made in Space. Actually, one of our largest contracts was a contract called Archinaut, where we would manufacture in large trusses and then assemble them to a satellite. And kind of it's still in development now as a part of Redwire. It's an exciting program. And I think for this next decade, we'll definitely be using things like inflatables. And if I had to guess, it's probably the same for next decade. Maybe in the later half, like 15 years plus, that's when you could maybe see where you supplement. But I think you would still always want to have inflatable systems just because it's very cost effective for things like lifeboats or farms or backup. Even if you had the most optimal in-space manufacturing system, I still think this is like a core piece of the space architecture for cities on the moon and things of that nature.
We talked about in space, are things free floating or attached to any other structure. How is it to bring an inflatable structure to Mars? Is that maybe also imaginable as part of the Artemis settlement? How flexible is that also on another soil?
Great question, Maxim. Maybe if you want to take this one.
Yes, from a lunar and Mars point of view, ultimately, that's one of the key venues that we're actually looking at. There would be no difference in general. You would adapt things like radiation shielding, debris shielding in accordance with different space environment. Beyond that, the pressure shell would basically stay the same to withstand the differential pressure needed for a breathing atmosphere. The interesting thing for us, which is very interesting, and this goes back to NASA, to programs that we worked on in R&D programs starting about 15 years ago, was our architecture, like I mentioned to you before, is isotensoid. The loads are only borne in one direction. And what that basically allows us to do is you can basically stick this in a lava tube on the moon, which is an absolutely huge advantage because it's a conformal architecture. Conformal architecture is, you think that any inflatable is conformable, but it's not that simple, especially when it's pressurized. If it's soft, and great, but if it's that level of pressure, so that would be a great benefit because of the radiation protection that we have. And if there's meteoroid activity, that's one of the first potential. If there was an easy way or straightforward way to get a human habitat in a lava tube, which is with this type of architecture, that would be a very logical place for the initial forays.
That's interesting. Aaron, anything to add on that?
I definitely want to add that the moon holds a special place to my heart. I normally have a photo of the moon looking at Earth in the background because my friends call me Mr. Moon because I like to tell people that my dream is to work on technologies that are going to enable a city on the moon one day. And I think that this is one of the, if not the core centerpiece and over the next decade and probably two. And if you think of how big the architecture can get, tens of thousands of cubic meters housing hundreds of people in one module, then you can inflate things like the walls, the furniture, the piping. You can inflate a lot more than you actually think and really getting a bang for buck. I get super excited about the future of max space and what we're enabling and how that'll enable, whether it's Artemis or Moon Village 2 or whatever that city will be, of hundreds of people on there. And it's just going to be so exciting. When I think about it, you go out at night, you look up at the moon and you can imagine it's honestly one of my driving factors of working on max space.
As you might know, I'm ex-PT scientist. I know what you're talking about and where your heart beats. Where's the company at the moment as we speak?
We announced who we are at Space Symposium. We basically launched the company last year to commercialize technology that Maxim has been developing now for decades in perfecting. And since then, we built our first module of our first ground unit that will be going to space within the next 2 years. We're manifested on a SpaceX rocket, and we are winning some Space Force contracts as well and getting a lot of gearing up for commercial and civil space customer kind of traction. And a lot of progress has happened in 1 year since we started the company.
How is the company funded today?
I wrote the first check on investing in the company, and then we raised an undisclosed kind of seed round, which was enough to build our flight unit module and get the manifest on SpaceX.
And is it pure America or North America focus, or are you also open to work with the rest of the world? Or to rephrase the question, how much ITAR is in it?
Yeah, no, we think we can work globally, within obvious limits. And of course, I actually think a big use case of space station modules in the future will be different countries having their own stations and their own almost embassies, have you will, in space. And it's definitely something that we are exploring.
Very interesting. What can we expect from you guys in the next 12 months? Because you said in the next 2 years you will launch. So what will happen in the next 12 months?
Yeah, mainly we'll be heads down, testing our module more, building out for the launch. We either have built or more likely probably building our larger modules and looking at what that will end up becoming and gearing up. And right now it's just really focused on getting the launch of our hardware.
There's one thing I know that we didn't touch on, and Aaron couldn't know that because he wasn't there for the boring technical bit. It's the thing about safety, because Aaron's always reminding me to say something about that. But again, that concept of when you say inflatable, that's why we often use expandable. I don't care, you could use inflatable, expandable, but you often use expandable just because it gives a connotation. It removes the sensitivity of, you put a pin in something that's inflatable and high pressure, it's going to pop. In reality, you're undoubtedly aware of that, Torsten, but the inflatable architecture is definitely a big step ahead of metallic when it comes for a habitation module, when it comes to protection against debris. It's like a monstrous bulletproof vest. The outside of our module is probably 40 centimeters at least thick, with multiple ballistic shielding layers that are like a bed from all kinds of exotic materials that can protect against penetration. And if anything gets through, the energy it destroys the particle, creates a debris cone. And then there's about, I believe on the current design, like 12 different catch layers to dissipate and catch. You don't have that benefit with the metallic structures. Mm-hmm. So that's a big deal. It's to the extent that we've been hired, for example, by the military to look at using that technology terrestrially, because it works way better than, for a lot of applications, better than composites, metallic shielding. So definitely a big advantage there.
Yeah, I think it's an absolute wonderful point that Maxim is bringing up there. Often think, hey, it's going to pop on me. And it's the first thing they think when they hear the word inflatable. It's kind of part of the reason, like Max said, we use expandables. Yeah, that's a great point. Any kind of closing thoughts? I personally get really excited about the future of space flight and human space flight. As somebody who Made in Space was in maybe cohort 1 of space startups, with groups like Planet Labs and Satellogic and a few others. I look at Blue Origin and SpaceX as like Virgin as cohort 0. And you're just seeing the accelerated pace of companies working in space and trying to change the game. I think we're in an exciting space boom right now that I'm really happy to be a part of.
Some final thoughts from you, Maxim?
I think the only final thought is probably for you personally, because you can get a view.
Oh, damn it. It's really there.
It is really here.
Yeah.
It is real. Like the money we put down on the SpaceX launch, it's real. And that's, I think, a real discriminator for us, because everybody says, yeah, we'll launch here or there, or then you know exactly what that's like. But when you actually put your pennies down, put a lot of money down on the launch, and you actually have the full fidelity hardware, that's different. It's very real.
Maxim, Aaron, thank you very much for your time and for this fantastic interview. I really enjoyed the time here with you and learning so much about what's coming up. And I'm looking forward to see it fly and see it in space. I think as much as you do. Thank you very much.
Thanks so much, Torsten. It was a real pleasure.
Thank you, Torsten. Have a great day.
If you have further questions, reach out to us at radio@SpaceWatch.Global. If you like these or other episodes of Space Café Radio, leave us a rating on your preferred podcast platform. It is the currency of today. And if you want to stay on the pulse of the space industry, please visit our website at www.SpaceWatch.Global and subscribe to our newsletters. And of course, don't forget to become a Space Watcher. I'm Torsten Kriening, publisher at SpaceWatch.Global, your independent perspective on space.